Alright, how's everyone doing? Let's go back up to the top here. So this is information theory 4. Why comparison sorts are always order of n log n. Alright, so the short answer is you have a list of length n. Well, we've covered. So comparison is asking a sequence of binary questions to figure out which of n factorial possible permutations of the input list is the correct permutation. So there's list of length n, there's n factorial possible permutation. So permutation, think shuffle, way to shuffle it. There's n factorial. So if there's a list of length 5, there's 120 different ways to shuffle that. And a priori, they're all equally likely. So the probability, so at the end of the day, you draw a binary tree. Every stem in the binary tree is a comparison, and every leaf corresponds to one of the permutations of the input list. They are all equally likely. All of the possible permutations are equally likely before you know any more information. And so the probability distribution is a uniform distribution with probability 1 over n factorial. Well, we covered in another video, or you just use the formula for entropy, the binary entropy of a uniform distribution of probability 1 over n factorial is the log of n factorial. Now remember, the binary entropy is the minimum average number of questions, binary questions, you need to ask in order to find which leaf on the binary tree you're at. So so if you were assigning a code to every leaf on the binary tree using the procedure from the Huffman tree video, this is the minimum average, the best arrangement of questions such that the average code length is minimum. That's what the entropy is. And so what this is saying is any algorithm, on average, you're never going to be able to beat the binary logarithm of n factorial questions on average. So you design some comparison sorting algorithm, on average, it is going to have to do logarithm of n factorial comparisons in order to figure out which list is the input list. That is the lower bound. You are never going to come up with an algorithm that on average is going to have to ask fewer than n factorial questions, log of n factorial questions, or do fewer than log of n factorial comparisons in order to ascertain. Sorry I'm repeating myself, but it's sort of important to get this clear, and repeating helps you remember. Anyway, so by the properties of logarithms, so this n factorial, that's n times n minus 1 times n minus 2, etc., all the way down to 1. By the properties of logs, that splits into a sum. And then, well, log of n minus 1, that's strictly less than the log of n. Similarly, log of n minus 2, that's strictly less than the log of n. So this is less than n copies of log of n. So that's why, binary entropy of a uniform distribution on n factorial, that is less than, strictly speaking, it is less than n log n, where n log base 2. Therefore, binary entropy on 1 over n factorial uniform distribution, that function is of order n log n. Now that's what is meant by comparison sort algorithms are of order n log n, which means the number of comparisons grows of order n log n. Now, what does of order mean? That's part of the longer answer. So again, the best case average number of comparisons is of order n log n. So what the hell does of order mean? Okay, so it actually means something really precise, and if you know what it means really precisely, it kind of helps disambiguate the kind of fuzziness, because you kind of know what order means, but not really. So generally, G is of order f if both of these are functions from, say, the natural numbers to non-negative real numbers. G is of order f if there exists some m and number c, which is a positive real number, such that for all n bigger than m, g of n is less than c of f of n. So maybe write this out and kind of see how the logic connects. There's a lot of symbols here, but it means something very simple. G is of order f if G is eventually bounded above by a positive constant multiple of f. So that's what we showed here, which is that binary entropy is bounded above by a constant positive multiple of n log n. Note that every logarithm base, so log base 2, is a constant multiple away from log base e. And that's just the properties of logs, and I will show exactly what I mean by that in a minute. So again, in our example, G of n is the binary entropy of uniform distribution on 1 over n factorial, which, if you plug that into the formula, you get the binary logarithm of n factorial. F of n, so we want to show G is of order f. F of n is n log n. And then, of course, by the properties of logarithms, so notice that order n log n is irrespective of the base of the logarithm, and it's because of this property of logarithms, which I encourage you to, after this video, or maybe now, try just from the definition of logarithm as the inverse of exponentiation, prove that this is true. It's going to help if you move log foo of bar over here. In other words, all log-based functions are constant multiple away from each other. Alright, and maybe I should have led with this, but it didn't really kind of fit into the beginning of the video. I kind of want to just get straight into the reasoning. But I should show an example of a comparison sort if you're completely lost. So the example I'm going to use is quicksort, because, well, everybody likes quicksort. Alright, so this is a eScript, Erlang script. First line is user bin nv eScript, so that's a crunch bang. Mode compile says compile this before trying to run it. So here's the quicksort algorithm. Quicksort on the empty list returns the empty list. Great. Quicksort on a list that is non-empty, so it has something prepended onto the rest. Who really cares what the rest is? Okay, and so what it ends up doing, let's just look at the bottom of the function. Quicksorts the left, plus everything that's equal to me, plus quicksort everything to the right of me. So the sorted if you get a non-empty list, you pick out everything that's to the left of the first element, everything that's to the right of the first element, sort everything to the left, sort everything to the right, and then everything, of course, that's equal to the first element, and then you just put those in order. So quicksort the left, plus everything that's equal to me, so eq is y such that y is from rest and y is equal to x. Left is y such that y is from rest and y is less than x. Right is y such that y is from rest and x is less than y. Quicksort the left, plus everything that's equal to me, plus quicksort the right. And then QSP, this quicksorts the input list and then prints it. And then main, so we're just going to test it on a couple of input lists. And let's just run it. There it goes, it sorts the lists. Alright, that's all I wanted to talk about. Thank you for watching.